time, we're talking...
Science time,
we're talking about collision. So please title... This is going to be... This is the purpose of this lesson, in my estimation, in your book, is to reinforce the ideas from the previous 3 lessons. This is lesson 4 from Module K, Unit 1. The purpose of this is to reinforce the ideas from the previous 3 lessons and to give you a hands-on example, which is the egg drop lab, which is what we have already done, but we will talk about some more. But we're talking about collisions, and we're going to talk about, if I say this is a review of the previous 3 lessons, guess what we're probably reviewing as we talk about collisions? Forces, and specifically, what ideas about forces? Newton's laws. Let's talk about each of Newton's laws as it refers to collision. So let's go through them all. Tell me what's Newton's. This is, if I'm not mistaken, this is the 3rd time I'm writing Newton's first law on the board for you all. And I think it's the 10th or 11th time I'm writing it on the board this year. Newton's first law. Let's say it first in one word because I like that, Kesslin.
An object in motion.
No, that's way more than one word. Inertia. Now let's say it in many words, and you write it down, but I'm not going to because I've already done it and it's already on video. So sue me. Don't sue me. Gunnar, what is it?
An object in motion tends to stay in motion, and an object at rest tends to stay at rest unless acted upon by an
An object in motion tends to stay in motion, and an object at rest tends to stay at rest unless acted upon by an outside force. So how does that apply to collisions? Collisions? First of all, let's rewind a couple steps. What is a collision?
A collision is when 2 objects collide.
True, but let's try not to use the verb as we describe the noun.
Go into each other.
Go into each other. Yuck. Whitley, what?
To hit each other.
Yeah, they're okay.
To slam
into, you're making it even less scientific. What can we say? Hit is fine, but what's a more scientific way? They come into...
To boom.
Thank you, Faith. Let's write it like that. Collision. 2, we could say or more. We're going to deal with only 2 in this class, but 2 or more objects moving into contact with one another. So how does Newton's first law apply to this? Well, an object in motion tends to stay in motion, and an object at rest tends to stay at rest unless acted upon by an unbalanced force. So if we have 2 objects and they're on what we might call, in seafaring, a collision course, this one is moving that way, this one is moving that way.
What's that word?
2
I don't know.
objects moving in contact with another.
So they're on a collision course. They're going to collide. They're moving toward each other. They're moving toward each other. How does that apply to Newton's first law? Gunnar, you already answered one. Let's let someone else have a chance. How does that apply to Newton's first law? First of all, using part of Newton's first law, what are these 2 objects like? They're already, these 2 objects are...
Staying in motion.
Please. They're in motion. These 2 objects are in motion. So according to Newton's first law, they will do what? Stay in motion. So if this is time 1, at time 2, what will they be like? Well, they'll be a little bit closer together, won't they?
So friction can cause an unbalanced force that causes this to stop?
Friction can cause an unbalanced force. In this case, we're going to assume there's no friction. And then at time 3, if they're still in motion, because Newton's first law says they stay in motion, what are they going to be doing?
Colliding.
Yeah, they're going to be touching. They're going to be in contact. I drew them kind of inside of each other. They're going to be in contact. Now, as soon as they touch, what part of Newton's first law is now happening? They are acted upon what?
They are acted upon by an unbalanced force.
Right. As soon as they touch, now they're acted upon by an unbalanced force. God bless you. If we label them A and B, A puts a force on B, and
B
puts a force
on A.
On A. What does this remind us of? We were talking about Newton's first law, but what does this remind us of? This one reminds us of Newton's third law, so we've kind of accidentally skipped ahead. Newton's third law, but this is all happening at once. Newton's third law.
Every action has an equal and opposite.
Right. So A puts a force on B, and B puts a force on A. And how would we describe that force broadly? It would be what part of Newton's first law? It's what kind of force?
Collision.
Sure, but what part of Newton's first law? We're using words from Newton's first law. Yes, Woodley, try again. What kind of force would this be?
For every action there is an opposite reaction.
That's Newton's third law. But what part of Newton's third law is this force? Fate, what kind of force is it?
It is an unbalanced
It's an
force.
unbalanced force. It's an unbalanced force.
I
So will they stay in motion now that an unbalanced force is acting on them? No. First they're going to do what? For just a split second they're going to,
Expand.
golly, I hope not. They won't change sides now. They're going to, okay, for a split second they will probably deform a little bit, at least depending on what the balls are made out of. But they will also, for a split second,
They will
stop. They'll stop. And if the object was moving, and now it's stopped, has its motion changed?
Oh.
Yes.
Yeah.
Wow.
Really?
Let's try again. You're right. Whitley, that was... Whitley lost her own mind trying to say the wrong answer. If the objects were moving, and now they're stopped, has their motion changed?
Yes.
Yes, and what do we call a change in motion?
Acceleration.
Yes. Change in motion equals acceleration. And what does that remind us of? Newton's second law. What? Newton's second law. They're all in this, aren't they? Newton's second law. We're going to do another example here. But then, so for that split second they're stopped. Their motion has changed so that they've stopped. And now in the next split second, time 4, how will they be moving? Yeah, the opposite direction. Opposite direction. Because B put a force on A this way, now A is moving how? The other direction.
The direction
What
that
it-
B put the force on.
What is Newton's second law?
We're going to get back to that, but for now it's enough for you to write down that this change in motion acceleration relates to Newton's second law, but we will talk about it in a second. This is all, for now we're primarily focusing on Newton's first law. So these objects were in motion,
But no.
and then an unbalanced force acted on them, so they stopped,
No.
and then that unbalanced force caused them to change their motion to the other direction, okay? An object in motion tends to stay in motion, and an object at rest tends to stay at rest unless acted upon by an unbalanced force. That's inertia, and that's Newton's first law.
Is that the exact definition though? Because I looked it up yesterday and there was a bunch of different ones.
For Newton's first law, he would have written it originally in Latin, so these would be just different translations.
Oh, okay.
Yeah.
What did the unbalanced force do?
The unbalanced force caused them to change their motion to be the opposite
What
direction.
year was Newton?
1650 something, I think.
Was Latin still like a thing?
Yeah, he would have primarily probably spoken English as his first language. It would have been what we call Middle English, but all the academic and religious texts would have been in Latin. Latin was he may
I
not
thought it
have,
died out far
he
before
may
that.
not have even been able to write English. I don't know. Someone knows, but it isn't me. But he wrote his texts in Latin to be shared with
Well, that was
the other
like
people.
the primary language.
Yeah, it was the academic and religious language. So anyway, so Newton's first law, they were in motion, so they tended to continue in motion until an unbalanced force acted on them and their motion changed. Okay, and then time 4, for the rest of eternity, if these are the only two objects in our universe, for the rest of eternity they'll be doing what?
Continue going that
Yeah.
way forever.
They'll be moving in a straight line at a constant speed forever. In
Like,
reality,
never stopping?
they would never ever stop.
Will it as the universe expands, it'll just keep on going forever?
Yeah, if these were the only two objects in the universe, and this is the only event that ever happened in the universe, they would just keep on moving in their opposite directions forever.
But would
And there
this
was no
cause
gravity.
And then there's
another
gravitational
event to
pull.
happen?
You're right, yeah. In the real universe, these would eventually slow down or crash or something else, but we're not talking about that. We're just talking about this. We're trying to keep things simple at this point. Okay, let's erase all this. What can you do, just BT dub, what can you do if you didn't want me to erase this just now, later, after class?
Watch the
Yeah,
video.
watch the video and pause it. Okay, so now, we talked about both of these a little bit, but now let's talk about Newton's second law as it relates to collisions. Newton's second law. Remind me, what was Newton's second law? Let's do it this time in words first. That's not words. I mean, those are letters, but I forget so much from Whitley and Fate and Gunner today. Haley,
I forgot.
An unbalanced force cause. Once again, can you-
you're right.
Okay. An unbalanced force causes an object to accelerate in the same direction
Yep.
as.
So in words, an unbalanced force causes an object to accelerate in the same direction as the unbalanced force. So if the unbalanced force that I put on my stand
Wait.
is south, what direction does it accelerate?
South.
South. And acceleration is a
Change.
change in motion. So it changes its motion to be south, right?
Sorry, what is second law?
The second law is an unbalanced force causes an acceleration in the same direction as the unbalanced force. So unbalanced force and acceleration are in the same direction. How can we write that as a math equation? Because it depends on one other thing too. Kimber.
F equals M.
F equals ma. I didn't think I had to point this out, but what mathematical operation is happening between m and a?
Multiplication.
Multiplication. F equals
We should
ma.
know that if a arrow is next to
So,
A lot of times I put arrows over those indicating that these things have directions. Newton's second law was, someone else say it. I said it so many times already, not you, Gunnar. Hunter.
An unbalanced force causing an acceleration in the same direction as the unbalanced force. Is that what you said?
Unbalanced force and acceleration are in the same direction. So, back to our collision. I'm just going to keep drawing balls. Back to our collision. We have the same collision happening. Okay, so everything's the same. Now think just about their masses. Let's say that, just to complicate things a little bit, let's make the one ball bigger than the other. Let's say this has mass equals 2x, and this one has mass equals x. So basically, I don't care about the actual numbers, what I'm saying here. What am I saying? This ball has what the mass of this ball?
double.
Twice the mass of this ball. Double the mass of this ball. So this one has twice the mass. So if F equals ma is true, how can I symbolize it using my equation that this one has twice the mass?
You can
What I like to do, first of all, back to Newton, I said that 13 times now, first of all, but this is now, by this time it's like 13th of all. 13th of all, when they collide, what's law of Newton's tells us that the forces are the same on each other?
no two.
No.
Three.
Newton's third law says that for every action there's an equal and opposite reaction. We'll get to that in a second. But the same force is going to be on both of them. The same F, right? The same size of F. What is different about the F? It's the same size, but it's what? No?
It's greater.
No, it's the same size. The same size of F.
Volume.
But it's what? What's different about the forces? They're equal in magnitude, but
Different acceleration.
different in... No.
Position.
No.
Weight. Gravity.
Different in direction.
Yeah.
Accelerate.
It's specifically, their directions are different, but they're specifically what?
Acceleration.
Ty, we talked about this one earlier. They have the same force, but it acts in what direction?
Opposite.
Opposite directions. It acts in opposite directions. So this one will have a force that way, and this one will have a force that way. But it's the same size of force. Now this one has a little baby mass, and this one has a great big daddy mass. Okay? They're going to be in opposite directions, but it's the same force. Okay? Same force. Are you with me so far?
Yes.
When they bonk, same force. What's going to be true of the accelerations? How is their motion going to change? Think about it conceptually. Which one is going to have a greater change in motion? The little mass or the big mass?
The little mass.
The little mass will have a greater change in motion. What do we call change in motion?
Acceleration.
Acceleration.
So how should I draw the A over here? Big or small?
Yay.
Uh-oh,
That would
there's a
be
disagreement.
big.
Raise your hand if you think big. Raise your hand if you think little. Oh, good. Okay, so there wasn't actually a disagreement. It's going to have a great big acceleration.
And the big.
And what direction is the acceleration going to be? The same direction as the unbalanced force. And this one's going to have the great big M is going to have a,
Little baby.
and it's going to be in the same direction as that force. So after our time 4 or whatever we had said, now the little baby one is going to be moving quite a lot that direction, and the big daddy one is going to be moving not very much in that direction. Because they've collided here. I just drew that. It's supposed to be two
So if
balls.
they collide, they go in opposite direction. We got it off the wrong way.
We say, look, for the same force, the littler the mass is, the bigger the acceleration is. We talked about this at the beginning of the year. What kind of proportionality is that? Remember we talked about scale, proportion, and quantity when we did the CCCs? Do you remember what kind of proportionality that is? When the mass gets smaller,
Expand.
the acceleration gets bigger. Is it, what kind of proportional? It's inversely proportional. Mass and acceleration are inversely proportional. So if force stays the same and the mass gets smaller, the acceleration gets bigger.
What's that word?
And if mass gets bigger, the acceleration gets smaller. I don't know. You can't just say, what's that word? I don't know what you're talking about.
I'm talking about the word below the.
Inversely?
Yeah, yeah.
Inversely. Your book says this, just so that I can make sure that we're all on the same page. Many collisions. How many? Many collisions involve objects with different masses. We know that each ball in the collision will experience equal and opposite force. So I'm not wrong, the book says it too. Equal and opposite force. From Newton's second law, we know that the acceleration of an object depends on its mass and the applied force. How will the relationship affect a collision between two objects with different masses? Well, what's the answer? How will the collision, sorry, what was that? How will that relationship affect a collision between two objects with different masses? What's the answer?
There will be different accelerations.
Exactly. There'll be different accelerations, and the accelerations will be inversely proportional to the mass. Bigger mass, lower acceleration. Smaller mass, higher acceleration. Okay, that's Newton's second law. And the direction is important too. They are in opposite directions. Okay? Let's move on. Newton's third law. Newton's third law. For every action,
There is an equal and opposite reaction.
What do we call these things together? This is a or an what? When there's two, there's an action and a reaction, we call them together a or an. You let me down again, worse. Interaction. Interaction.
What's that A?
For every action, there is an equal and opposite reaction, which together they're called an interaction. We've already talked about this one twice now because we talked about it on the other two. But it says that if balls are touching, if the balls are running into each other and they're in contact, or touching is kind of a loose word, but if they're in contact, this one is going to put a force on the other one, and the other one is going to put a force back on him. If A puts a force X on B, B puts a force X on A. Why did I use X for both? What's the same about them? Same what?
Forward.
Same. Same. What's the same about the forces?
Same gravity.
Same what, Kimber? Yeah, they're not balanced because they act on two separate objects, but they're the same size. Opposite what?
Direction.
Direction. So then the next time, if this one put a force on this one, which way is that one going to go? Oop. If that one put a force on that one, that one's going to go that way.
Can I ask a question?
Of course not, Drew.
When is physics over? Like,
Physics is never over. I know what you're talking about, though. We're going to be done with this module probably in a couple months.
couple months.
And actually, the rest of your modules, the next module is also physics, but it's not kinematics. Kinematics is the study of motion. The next module is going to be waves, which is different. And then we're going to do some bioscience, and then we'll do space science. So you get a little, it's like the appetizer sample. You get a little bit of all the sciences. And then you can specify what sciences you want to do as you progress in your education. Anyhow, Newton's third law is that for every action there's an equal and opposite reaction. Equal in what? Equal in. No, I'm saying equal in what? What's equal about them? The size. The magnitude of the force is the same. What's opposite about them? Direction. Fate.
They already said it.
I already said. Oh, okay. I already answered your question. I was worried you were talking about the video and that I wasn't starting the video somehow. No, but that's good. Energy, it says. Energy. We haven't talked about energy yet, so let's talk about energy. Energy in collisions. I'm just going to read you this, and then I'm going to read it, you're going to listen, and then we're all going to synthesize, and by that I mean we're going to take in what I read and you listened to, and then we're all going to figure out what's important about it, and we're going to synthesize it, put it all together, and we're going to put it on the board, okay? Ready? Are you ready to listen to me read?
Yes, sir.
Show me the irregular smoothly. Objects and systems may contain different amounts and types of energy. Okay, Kimber. When an object is moving, it has kinetic energy. Write that down. When an object is moving, it has kinetic energy. What happens to this energy during a collision? It says. It says
We
this.
wouldn't.
It
What?
says make this.
When an object
We don't have to write down the whole thing. It's in your. You have access to this. You don't have to write this whole thing down. I just want you to listen to me.
When an object is moving.
When an object is moving, it has kinetic energy.
It has.
What happens? I specifically said you don't have to write this down. We're gonna figure out what we need to write
this
down.
down.
No, I said you don't have to write this down. We're going to figure out what to write down after I read this. Right now, you're supposed to just be listening.
No, you said the
Listen.
phrase and you're like,
Oh.
write this down.
Anyway, when an object is moving, it has kinetic energy. What happens to this energy during a collision? Some of the energy remains with the object. Some of the energy is transferred from one object to another during the collision. Some of the energy is transformed into other forms, such as sound or thermal energy.
Mr. Kine?
Didn't say that.
Okay. If an object in a collision is made of an elastic material, the energy may be temporarily stored as elastic potential energy as the object deforms. So, what do we need to write down from that?
Energy.
So, what kind of energy did the balls have when they started out?
kinetic.
Kinetic. So, kinetic energy equals energy of motion. And then, as the collision occurs, in what we call a perfect collision, in a perfect collision, all of it would switch from one object to another.
Mr. Kine?
Okay.
You learning. So in a perfectly elastic collision, all of the energy would be transferred from one to another. But in the real world, some of that is lost. So kinetic energy is the energy of motion, but some energy in a collision is changed to what? What other kinds? What did it say? It said some of the energy is transferred from one object to another during a collision. Some of the energy is transformed into other forms such as sound or thermal energy. So it's changed to sound or thermal energy. And you know what sound is.
Yes.
If the balls hit, they make a sound. And that's a way of energy being lost. Energy is never technically lost, but it goes into the environment. What do we call it when they turn into thermal energy? This is going to... I think you'll be able to do this.
Is that a
What?
collision?
Like when friction, when you like.
Friction.
So
So when some of the energy, give me a second. When some of the energy that was motion energy, kinetic energy, changes to thermal energy, that's called friction. Kinetic energy is energy of motion. Some energy in a collision is changed to sound or thermal energy.
So thermal energy is friction, but what is sound energy?
Sound energy is sound
Sound
energy. And really friction, and the thing that was confusing you, Hunter, is that thermal energy is not friction. It's that friction is thermal energy. Friction is what we call the process of kinetic energy becoming thermal energy. You have questions?
What's that one?
Okay. It's gonna work.
It doesn't work.
Energy
Collision.
collisions.
Does anyone have any actual questions about the content?
Every
Shh. Does anyone have questions about the content?
changed.
What?
Changed.
What's that one?
Changed.
Oh.